Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to talk about the electric current, which is the movement of current itself. So before we get started, please consider subscribing as well as liking the video, as well as checking the description below for the notes in this entire discussion. So let's start by discussing the electric current itself. So the electric current is defined as the change of charge over the change of time. So this might be a little bit weird because what's changing in itself? Because what is exactly the change of current in here? In here what I what I mean by the change of charge is if I have this, let's say, material and I move it across with a certain velocity, so it has charge over a certain area. So after a certain amount of time, what's the accumulated charge that is scanned by this area? That's pretty much the idea. So if you actually try to take this change of time to be very small, you could get the definition to be the change of Q over the change of time, something like this. So in here, the easiest way to try to understand this concept is by actually dealing with the microscopic object itself. So an object here, let's state that it has electrons mostly, and it is going to be moving across a surface A. So let's state that I know the density to be n. So there's n electrons per unit volume, and this object is going to be moving at a certain velocity. So there is also going to be length here anyways. So the change of Q after an amount of time in which all of this object is transposed by L will be pretty much the entire charge of this entire surface, which will be n times q. Q is the charge. Multiply that by the volume, which is A times L. And you would divide this over the change of time, right? To get your current. So the change of time, pretty much from classical physics, no, classical mechanics, it will be the length over velocity. So this will obtain the NQ AV. So this is pretty much the definition of current in the small scale. So something to notice here is that if the charge is negative, that means that the velocity is going in the opposite direction of the current. So that's something interesting to actually think about. Another thing is when you're starting to deal with an entire object moving, if this bulk object is all moving at the same direction, there won't be a change in charge. So that's why a moving object doesn't truly mean that the change of Q is a value. But if I state that if I apply an electric field, positive charges are going to be moving in this direction and the negative charges are going to be moving at the opposite direction. And this will later cause a change in charge, as there is charge getting out, which is negative, so it will be plus, and there's charge moving in, which is already positive. So something interesting to ask is, what exactly is the velocity of the electron? Since you know that the temperature itself will imply that there's a velocity in the electrons, because pretty much electrons in a conductor are pretty much like gas. It can move around freely. Well, this velocity is different. Compare that to the velocity in the temperature. So the velocity in temperature is random. It's pretty much in any direction. Even though that it has an average value, but its direction is pretty much random. So if you sum them all up, it will be pretty much zero. And this is what you call as the v thermal. But there's also something which you call as the drift velocity, in which it is pretty much the entire bulk material is tending to move at a certain direction. That's the drift velocity. And you could actually determine that the maximum for the VD is VTH. This is a relation that you can gain by actually comparing the drift velocity as well as the thermal velocity. So we have already started to talk about this entire concept in the microscopic scale. So there's also another useful notation when you're dealing with microscopic objects, which is density itself. So for current, it is the current density, J. So current density is pretty much the current within a certain unit area, or you could just state that to be the I over A. But to be much more exact, I itself is the integral of J vector dot dA vector. So it's pretty much the density multiplied by an area. It's like flux. No, it's similar to flux. So pretty much the current is like flux, and the current density is pretty much like the electric field. It's like, but it's not the same. So that's like the analogy itself. And another thing to observe here is current is actually not a vector quantity. It's actually a scalar quantity. And this J vector has a direction. So how do you create a scalar object from a vector object is by actually doing a dot product. And this dot product is by the dA vector, or the area itself. And this area will later determine if your current is positive or negative. So if you define let's say your area to be in this direction, it will mean that the current is positive. But if you define your A vector to be at this direction, the current will be negative. So it's just a matter of convention. But normally we will just be using this type of convention, in which that you would be assuming that the A vector is in the direction of the J vector as well. So that's the idea. So just by trying to figure out what's the J of this simple assumption or this problem, the J is the NQVD. So that's pretty much after you're dividing it by area. So now you could actually quantify what is actually the current density. It's pretty much just the density of the charge carriers. Multiply that by the charge itself, multiply that by the tendency of movement, which is the drift velocity. So now I want to talk much more about conduction itself. So conduction. So how do you determine your J vector? Well, if you actually try to observe this in a lab system, you would normally apply an electric field first, and this will later result in a formation of the J vector, and it's actually proportional to each other by a factor called sigma. The sigma here is something which you call as conductivity, something that is normally used in material science. And if you have the sigma to be independent of E, this material is called as ohmic, while a dependent will mean that it's non-ohmic. So maybe for you who are already studying about electrical circuits, are much more familiar with the concept of resistance. So, what's resistance exactly? So, let's actually just do this idea. The E vector is something of the J vector. Well, the idea is that it's 1 over sigma, or I will call this value to be rho, which is actually 1 over sigma, right? This is something which you call as the resistivity, with units ohm meters. So, we have already talked about conductivity as well as the resistivity, which is concepts that are that are held by the material itself. It's like the property of the material. So, let's actually dive a little bit deeper into the material science, and let's actually discuss about why conduction could happen. So let's first discuss about metals. So metals are pretty much materials in which the electrons are free. So if you already have this bulk material, you could later express this when you deal with quantum physics, is that the electrons are pretty much free. So the electrons can move pretty much anywhere. And if you actually apply an electric field, there will later be certain movements of this electron, even though that it's a little bit random, but its tendency will later be related to the drift velocity. So there's a very interesting question when you're dealing with this model. If you apply an electric field towards a electron, you would know that the force is pretty much the charge of the electron, multiply that by the electric field. And this is pretty much ma. So that means that the charge itself is accelerating. And if there's no other force counteracting this acceleration, its velocity is pretty much going to go towards infinity. So there has to be something that's blocking its maximum velocity. And this is the idea of collision between the lattice. So this collision between the lattice will later be related to something which you call as the phonon. So technically the electrons are not really colliding with the lattice itself, but it is transferring its energy through phonons, which is pretty much particle-like substances, or particle wave-like substances, pretty much very similar to photons. But I will later discuss much more about phonons a little bit when we're dealing about quantum mechanics. But for now, we'll just say that it's exchanging energy with the lattice itself. So this pretty much dissipates its energy and thus having its final velocity. So there will be drift velocity. Thus, there's a current in the opposite direction since it's electrons. So that's the concept of conduction within metals. What about ionic solutions? Ionic solutions are pretty much solutions in which they have ions. So there are cations, the positive charges, as well as the anions, the negative charges. And pretty much the entire material itself is neutral, so there's an equal amount of these. But if you apply an electric field, some of them will move in one direction while the other move in the other direction. And this analogy is the definition that we have already tried to define, which is the J vector as well. So this is also the current density. So same idea. Why is the velocity not infinite? Well, it's all due to the collision between the ions, or even with the solution itself. Maybe there's H2O within the solution, so there's collision between the particles. So that's why your current can't be going towards infinity. So what about if we think about plasmas? So plasmas are pretty much gases that its electrons are pretty much free due to high energy. So high energy pretty much allows this electron to be free from its nucleus. So there will be negative charges in the surrounding. And applying an electric field, it has the same idea. There are movement in one direction, and this electron cloud will move in another direction. So this also creates this current. So mostly in here, we discuss about materials in which they have free charge carriers. But what about materials which doesn't have free charge carriers? So that's pretty much the idea of semiconductors itself. Semiconductors are pretty much materials that are not conductors but not insulators. So in here I have a lattice of silicon, and they all need to have an octet rule. That's pretty much what you get from chemistry. So let's just apply certain energy into this, but not high enough such that the silicon just by sudden turns into liquid. So I just want this energy to be high enough such that there will be multiple breaking of the bonds. So maybe this one will break, and this one will break, and this one could break, and maybe this one could even break. And if I also apply an electric field, let's say in this direction, this breaking of bonds will mean that there is electrons freely moving around, right? These electrons could later move to the bonding sites, and thus creating a current. Well, technically it should be at the opposite direction. So let's just do it like that. So you could see that there is movement of charges. But maybe you want your semiconductor itself, because of its interesting property, you want it to be conducting within low temperature or pretty much at low energy. So some ideas could include doping the silicon with certain materials. One of them is phosphorus. Phosphorus has 5 valence electrons, which means that it will later bond, and there will be a free electron moving around somewhere along there. This is what you call as n-type doping. N-type doping. So n-type doping is where you actually introduce another electron into your entire semiconductor. And this electron pretty much behaves like the free electrons here. So that means that the energy that you need to actually, well, the energy would be the same, but you don't need a high amount of energy such that there's multiple different breakings within your lattice. You only need a few amount, and then these free electrons will later move, thus creating a charge. Or another idea is to actually to dope your material, but instead of using phosphorus, let's just put in boron, because it has 3 valence electrons. So this means that our bonding wouldn't be complete. It is as if that we would have something which you call as a hole. So there's this bond in which that it's missing, but the entire material itself is neutral. So if I apply certain energy, there'll be some breaking, right? That means that there's free electrons, and these free electrons want to move towards this other bonding site, thus creating another charge. But instead of moving our charge, instead we're moving our hole around. So it is as if we are just moving this hole around, thus creating a charge, but a negative mass charge. So with this, we could actually start to develop a very interesting type of material. Let's just design a material such that one half is p-type and then the other is n-type. So p-type is this other one here. This is p-type since you remove an electron. So it's technically a little bit much more positive. So let's just actually apply a battery. Well, a battery. Like that. So in the p-type, there should be holes, right? And then for the n-type, there should be electrons. So there's a positive terminal as well as the negative terminal. So first of all, this electron would want to jump here because there's a empty state. But also, since the p-type semiconductor itself is also a conductor at this temperature, it means that the electrons could move, thus being able to move around its electron to be at here as well. And there will later be also movement towards this boundary as well. So you could see that if I put the P and the N together, and I put the positive terminal at the P terminal, there's movement of charge. But what about if I actually flip this around? Instead, I have negative here and positive here. So that's actually the voltage. So same idea. We would have electrons here as well as holes. So now, we do know that the electrons want to fill because there's empty space. But because of this negative terminal, it actually pushes the electron much more inwards, thus actually creating some form of tension between the P and the N type. And this is also true for the hole itself. So it also like forms certain holes, and holes want to move in the opposite direction. So there is this region in which you call this region as the depletion region. So this is where it's pretty much that there is like a insulator in between the P and the N, even though that the P and the N itself are pretty much like conductors. And this is the idea of a PN junction. So a PN junction literally is a one-way gate for current. And this is very useful when you're doing electronics, in which you only want a certain movement of charge, otherwise that it could actually destroy a certain component. So this is something useful for you to understand. Another type of material, or much more specifically a tool, is the transistor. So let's just have a shape, something like this. So I have P-type here, and there are N-types here. And I'll just put the charge there. So same logic. So N going to P, this is positive terminal, this is negative terminal. This can actually transfer its electrons, so it's totally fine. But for this one, it couldn't actually get any electron to go into the P region, thus actually creating some form of a insulator. So this is like as if the gate is off. So the current itself is 0. But what if I actually apply a voltage here? That means that this will be higher in voltage, so that means that electrons want to move in this direction. So it is pretty much contained within this very small surface. What you have here is something which is like a N-type conductor, a N-type semiconductor, which bridges between the N as well as the other N. And since you know that the N itself, as the entire object, is a conductor, that means that charge could exist. So this is the idea of pretty much a lever or a button in a electrical circuit. And this is what is normally used when you're doing logic inside your computer. So there are lots of these types of transistors. There are probably millions or even trillions, and they each actually do computations for you. So it's like the logic that you need, like binary, it's on or off. So that's some uses and understanding of the semiconductor. Finally, there is there is also a certain kind there's a certain kind of material which you call as a superconductor. So superconductors, I won't fully discuss the technical side of superconductors, but pretty much it has a property that the rho is pretty much zero. So so without even applying an electric field, there could be a current inside of this superconductor, and this only works low at low temperatures for certain materials. And currently, there is research when you're trying to create a superconductor within room temperature. So this idea revolves around putting certain alloys just to design a superconductor that will later be useful for our daily life. So we have mostly discussed about material science. So now let's actually just jump into one law that is normally used in electrical engineering, which is Ohm's law. So I might have already given Ohm's law, which is the E vector is the rho times the J vector. So here's something that I want to actually to derive. So E vector itself, so it's E vector, multiply that the by the displacement L, is what you know as voltage. It's pretty much the definition. Well, technically it's the negative, but I won't fully discuss a lot about the signs. So E vector multiply that by the length, it's the voltage. And also the J vector, multiply that by the area, is what you know as the current. Well, actually this should be E vector and negative delta nabla vector V. So this pretty much gives the relation of negative V times L, V over L technically. So these two, when you actually try to combine this into Ohm's law, you would get, I'll just take the positive values. It'll be V over L to be equal to rho I over A. So we do see that a relation of voltage as well as current in terms of this rho L over A. And this rho L over A is what you call as resistance. So resistance itself is pretty much a macroscopic property. So it depends on the shape, it depends on the material, it depends on what type of material that you have mixed in between those two, and it can all be computed by only understanding resistivity. But if you're an electrical engineer, you don't care about the material, you just need to use it. So the resistance itself has units of ohms, which is the volt over amperes. And this might seem a little bit a little bit familiar, but it has a it has a certain idea that voltage is a function of current, which is not entirely the case. In fact, the much more better way for you to write Ohm's law is I equals to V over R. And why is that? Current is pretty much the function of the potential difference. That's pretty much the idea. And it is actually divided by a certain proportionality constant. And don't forget about last time in which we discuss about ohmic as well as non-ohmic materials. And in here, certain certain components are non-ohmic, in which they depend on the voltage, something like the p-n junction, while others are ohmic, such as resistors. Well, technically, after a certain amount of temperature. So this pretty much only works at very small intervals. But it works if you're dealing with electrical engineering, because you're not dealing with high power or high current. So there are certain ideas that you could actually use when you're describing a circuit, thanks to this idea of Ohm's law. One of them is the open circuit. So an open circuit is where current is zero, but there's a voltage, and voltage is voltage. So this idea means that there's a resistance of pretty much infinite. Well, pretty much very big. So this is the idea of a open circuit, is that there is a high resistance between one end as well as the other end. Another idea is short circuit. So short circuit pretty much means that the I is I, while the V is 0. Well, for a number to be for 0 to be divided by another number equaling to a number, it doesn't make sense unless if you're dealing with R equals to 0, or technically the limit. So this is where your resistance is pretty much 0. So even if you don't have voltage difference, there is still some current passing through. So those two notations are normally used when you're dealing with electrical circuits, in which short circuits could describe cables, while open circuits could represent two different nodes that are not attached. So finally, I want to discuss a little bit about the electric power itself. So how do you define electric power? Well, you should remember about power itself. Power is pretty much the change of energy over the change of time. And in here, the energy will be in the form of the electric potential energy, which is Q times V. So let's actually just assume constant voltage. So we won't deal with crazy types of voltages. Well, technically it should be dQV plus QdV, but in here I want to set the dV to be 0. So we would obtain a dQ over dt, multiply that by V. Now, this dQ over dt itself is something which you know as current. So you could write this as I times V for constant voltage anyways. Now, since you know Ohm's law, so for ohmic materials, you could actually deduce that the power could be written as I squared over R, or even B squared over R. So why do I start to discuss about electric power itself? So one idea is that sometimes that you could feel shocks when you touch a exposed wire. So the idea is there is let's say a plug here, and then there's wire. So sometimes like the wire itself has a exposed end. So you might accidentally touch this exposed end. So if you touch this exposed end here, you are pretty much grounded to the ground. So pretty much you have 0 volts, and then this is pretty much low as well as high, for example. So if you touch this piece of wire, you could have a potential difference between your body such that there is a current flowing through your body. And this could be dangerous or even fatal towards the human body, especially in humid conditions. So one way to actually to mitigate this hazard is by actually also supplying another another node which is already straight away connected to the ground. S- and and it already has a very low resistance compared that if you straight away touch it. And this actually saves human lives, since most of the current will later be directed straight away towards the ground instead of going through your body. So this is one of the safety features that engineers have created when they design plugs. So so electrical engineering is is one field in which you try to convert electrical engineering, no sorry, uh, electrical energy into something else. But they also try to protect human lives by also designing ways to prevent any dangerous events going on. So that's all for today's video. So I hope that this video describes a lot about the electric current, and don't forget to subscribe as well as like the video, and also please share this to your friends who need much more understanding in physics. So thank you very much, and I will see you on the next video.